Good afternoon and welcome to Georgia DNR's Lunch and Learn webinar. I'm Emily Wingo, the Georgia Department of Natural Resources Floodplain Unit. First, a little housekeeping. We are in listen-only mode, so please make sure your mic is muted. If you're having any Wi-Fi issues, you may want to turn off your camera and any other programs you have running. Please make note of the chat feature in either the upper right hand or lower right hand of your screen. Please use the chat for communication as we will not be taking questions by audio. Jim Kilinowski of Dewberry is monitoring the chat and will try to help you with any technical matters. Please be sure to post to everyone when using the chat. We are offering 1 hour of continuing education credit for CFMs. To receive the credit, you must be logged in separately, answer all poll questions during the session, and provide your name and email at the end of the presentation. Poll questions should appear as a pop-up on the screen, but may appear in the chat box. If you're having issues with the poll questions, please be sure to check that chat box and use the radio buttons to respond. A copy of the presentation will be emailed out to all attendees. Also, a survey link will be provided at the end of the presentation. We appreciate you completing the survey so that we may improve these webinars in the future. We are recording today's session, so please note that lovely little button up there saying that we're recording because we plan to post the video on georgiadfirm.com. Okay, with that, let's get started. Today we have a presentation about the application of base-level engineering for planning and design. Our presenters are Petya Dubrovsky-Ileva and Sam Fleming with Dewberry's Atlanta office. Petya is a water resources engineer. She has a BS, MS in civil and water resources engineering and has more than 20 years of experience. Her technical expertise includes 1D and 2D H&H modeling, stormwater infrastructure analysis and design, and dam breach modeling for various private and municipal clients in Georgia. Sam has over 25 years of experience in civil engineering. He has a BS and MS in civil engineering from the University of Alabama. He is a registered PE in Georgia and a Georgia Safe Dams Program Engineer of Record. Prior to joining Dewberry, Sam served 9 years with Gwinnett County's Department of Water Resources in their stormwater program. And with that, I'm now going to turn it over to Petya.
Thanks, Emily. Good afternoon, everyone. So today we're going to talk about the application of the base level engineering analysis for planning and design. We are going to provide an overview of the base level engineering studies developed in Georgia and how you can utilize the base level engineering analysis for planning and design. This is going to be applicable for floodplain administrators, community officials, also emergency managers, engineers and surveyors, which shouldn't be community officials, but they can also utilize the data from the base level engineering analysis to take more informed decisions when they're working on planning and design projects to make sure that they build a resilient community. And we'll have a section for questions and answers at the end of this presentation. First, to start with providing information, what is the base level engineering? So FEMA initiated the base level engineering projects in order to provide a watershed-wide and H&H analysis, which is cost-effective to identify the existing flooding risk in communities and that can be available to, again, community officials and, private engineers and surveyors to identify the existing flood hazard, also to evaluate the accuracy of existing flooding maps in the communities. The base level engineering analysis can also be used to initiate, basically identify the scopes for new flood risk projects and also to support floodplain management efforts in various communities within municipality. Where is base level engineering data currently available in Georgia? So the Georgia Department of Natural Resources has started funding base level engineering analysis projects since fiscal year 2019. So since fiscal year 2019 projects, a total of 25 Hook 8 white watersheds has been funded for base level engineering analysis. The majority of them are located in the southern part of Georgia, as you can see here on the map below. And yes,
Katie, I'm sorry to interrupt you. I'm not seeing your slide deck.
oh, sorry. What about now?
Yes, thank you.
Perfect. So, okay. So, again, a total of 25 Hook 8 white watersheds has been funded by the Georgia Department of Natural Resources. The majority of them, as you can see on the map, are located in the southern part of Georgia. And currently, 6 of those 25 Hook 8 white watersheds, the base level engineering analysis is completed. For the remaining watersheds, the base level engineering analysis is in progress. To receive the most up-to-date information about the status of the base level engineering in each of those scoped watersheds, I would recommend checking the Georgia DFIRM website and the BOE project area viewer and the dashboard that can give you the most up-to-date information. And links to this website are enclosed, will be basically provided to you further down in our presentation into the resource section. How are the base level engineering analysis developed in Georgia? So depending on the topographic conditions in each scoped watershed, the base level engineering analysis is using different engineering methodologies. So the two options are for 1D base level analysis and also for 2D base level analysis. For any watersheds which have characterized by steeper terrain and confined floodplains, we have utilized the 1D methodology to develop the H&H analysis. With the 1D methodology, we are using high resolution LiDAR topographic data to define the watershed boundaries and calculate the flows in the watershed. For the hydrology modeling, we're using a gridded approach. So for every stream in the watershed that has a drainage area of more than 0.1 square mile, flow is calculated using the gridded approach. The flows are calculated based on the regression equations, the applicable regression equations, urban or rural, depending on the existing development in the watershed. And if any USGS gauges are available in the watershed, gauge analysis is performed and also utilized to calculate the flows along the streams where gauges are available. The hydraulic modeling is utilizing the HECRA software. It's well-known software and it's been used for a while. So all the models for the BLE analysis are going to be using version 5.0 or newer of HECRA's model of the HECRA software. So the 1D modeling cross sections are being cut at the representative locations along the streams based on the LiDAR topographic data. No survey data is collected, so it's all based on the LiDAR topographic data. Structures are not modeled, like no survey data is collected for structures, but the impact of hydraulic structures is approximated by basically burning an opening through the road embankments to kind of represent any coverts in the road embankments. The size of the structures is approximated based on aerial imagery or LiDAR data. For the 2D base level engineering analysis, we apply this methodology for areas with a flatter terrain where we have more complex flooding conditions and interconnected floodplain. So just one second. Interconnected floodplain. This methodology incorporates the hydrologic and hydraulic modeling through the rain-on-grid methodology. With the recent advancement in the HACRAS software, we are performing the hydrologic and hydraulic modeling all in HACRAS. So for any base level engineering analysis funded by the fiscal year 20 or 21 project, the whole BOE modeling is going to be performed in HACRAS. With the older version of HACRAS for the fiscal year 19 projects, we use two US Army Corps of Engineers softwares to develop the analysis. The first software is HAC-HMS. This is the hydrology software. Basically, what we use this software for is to model the precipitation losses and determine the rainfall excess out of the HAC-HMS model. And then this rainfall excess was applied in HACRAS to model the propagation of flow in the watershed. So for the 2D analysis, hydraulic structures are not directly coded in the 2D analysis, but the impact of hydraulic structure is estimated. Again, what we did is like we burned slots through road embankments or railroad embankments in order to let the water accumulate downstream and hydroenforce basically the topographic data, and thus simulating the impact of hydraulic structures in the watershed. Our hydraulic modelings are calibrated after we develop the 2D analysis. We check or basically validate our hydraulic modeling, spot check it at several locations in the watershed. We extract flow hydrographs from the 2D model, and we compare that with the USGS regression equation estimates to check if our flows are within the upper and lower bounds of the USGS regression equations, or if gauge data is available, again, to make sure that we are within the upper and lower bounds of the gauge estimate. And some of the benefits of using a 2D analysis for the base level engineering is that it provides like actual accurate simulation of the complex flooding condition, again, in flat topographic regions. It provides it actually requires less model input, so basically fewer assumptions, provides connectivity throughout the watershed, it's efficient, and it's FEMA-approved methodology. The Georgia base level engineering analysis is incorporating various BLE enhancements compared to the regular base level engineering analysis that basically increase the accuracy of our modeling and incorporate further detail. As you can see on this slide, we have an example of a 2D mesh, original 2D mesh, where the sides of the 2D grids are not aligned with any significant topographic features in the terrain. Our automated tools are creating break lines at significant topographic features. As you can see here, we have a road crossing that break line is created along this road crossing. We also have a break line along the 1 square mile streams in the watershed. All these are enforced in the 2D meshes for the 2D domain in order to make sure that when the flow is flowing through this channel, the high point at the road embankment is going to be accurately represented in the model, and weir flow is going to occur only when the flow is higher than the top of this road embankment. Additional automated tools that were developed and incorporated in the base level engineering analysis is, as I mentioned, simulating the impact of the hydraulic structures. As you can see on the image on the right, we have tools that automatically create a burn, or like they burn a slot or like an opening through road embankments to let the water flow downstream and basically hydro-enforce the topographic data. The size of this opening, again, is not exact. It's approximated based on LiDAR data or aerial imagery. So once the base level engineering analysis is completed, the next step is to develop the floodplain mapping and the rest of the BLE products. So as I mentioned, for the analysis, we utilized high-resolution LiDAR topographic data. The same data is also used to plot the floodplain mapping and prepare the BLE deliverables. So for the base level engineering analysis, for the 1D and 2D analysis, we are modeling 9 storm events, with the more frequent storm event being the 20% event, and the less frequent storm event is the 0.2% event. We also include modeling for the 1% future land use conditions. We evaluate the potential for development, future development in the watershed, and if there is, more significant development expected in the watershed, the 1% future event is also included in our results. Along with these 9 storm events, we include some additional floodplain mapping, which is the freeboard analysis. As most of you are aware, the National Flood Insurance Program has identified the minimum requirements for regulating floodplain, but some communities have incorporated more stringent requirements for future developments, requiring providing a freeboard above the base flood elevation to kind of account for some uncertainty and provide additional safety. In order to help regulate any future developments, we have developed these 3 additional floodplain delineations, which are base flood elevation plus 1 feet, plus 2 feet, and plus 3 feet. We have all these floodplains are provided as part of our base level engineering analysis deliverables and are available for everyone to use. Just to clarify that we spend time cleaning up the 1% floodplain mapping, basically making sure that it's smoothed and we don't have like any kind of areas that are that require some additional details. So we did spend time of cleaning up and smoothing the 1% floodplain mapping. Some additional products that are developed as part of the BLE analysis are water surface elevation grids. Again, these are developed for all storm events, and they provide information about the water surface elevation in every single point of the floodplain. So you have 9 water surface elevation grids available. The depth grids are also available for all 9 storm events and are providing information about the depth of water in the floodplain. So this depth is based on subtracting the water surface elevation and subtracting the LiDAR topographic data from the water surface elevation. And also we have developed probability grids. So we have 2 probability grids. One is providing information about the % chance of flooding in every single year. And the second one is providing information about the % chance of flooding over 30-year periods, which is the typical mortgage life. For the 1% event, we also ran the flood boundary standards. The FEMA flood boundary standards check and make sure that our floodplain mapping is passing the required accuracy. Additionally, the 1% event has been subdivided into several categories based on cumulative drainage area to the particular point, and also based on the depth of flooding. As you can see here on the map to the right, we have the primary 1% floodplain shown in blue. This one has a drainage area of larger than 1 square mile and depth more than 1 foot. We also have in yellow identified floodplain areas where the average depth is less than 1 foot. We have in orange drainage areas that have less than 1 square mile. And in red, you can see areas that has a drainage area of less than 1 square mile and flooding depths of less than, average flooding depths of less than 1 foot. And with that, we are coming to our first poll question. So you can answer the poll question on the pop-up, or if you don't see the pop-up, you can use the radio buttons on the chat. So the first question is, Georgia base level engineering analysis is developed utilizing 1D and 2D modeling methodology.
And everyone, just remember, if you're wanting CFM credits, to please answer the question.
Probably a couple of more seconds on responding to this question.
All right, Peggy, it looks like it's kind of slowed down. If you want to go ahead and give us the wonderful answer.
Okay, so the answer to this question is true. Yes, we used 1D and 2D modeling methodology to develop the Georgia base level engineering analysis so far. And going to the next slide, we're gonna talk about the application of the base level engineering analysis for planning and design. So I just want to mention that the use of the base level engineering analysis and the results that we have with the different data sets, an estimated BFE is not required, but information is available and can help community officials and developers with various aspects of their everyday life, like making decisions about, planning and development, zoning, mitigation, emergency management, stormwater management. The data is available, and I also would like to mention that it has been developed following all the FEMA requirements for development of regulatory products, and is available to be incorporated if there are funding available, and if risk map is initiated in your community, the data is available. It can be incorporated into the FEMA maps. The BOE data can be used by different departments within a community, so it is recommended that once the base level engineering data is received, that the different departments are notified and the data is distributed to be used for planning and design projects. The first application of the base level engineering analysis is for zoning planning. The base level engineering analysis is providing spatial and visual representation of the existing flooding risk in areas that were previously not mapped as a special flood hazard area. As you can see here on the examples on the left, you have a parcel that was previously located in a unshaded zone X. So no flood risk information was available for this lot. If you overlay the 1% base level engineering floodplain mapping with this parcel, you can see that majority of this parcel is included in the 1% base level engineering floodplain mapping. So there is an existing flood risk for this parcel. So the base level engineering analysis can be used by community officials and zoning department to evaluate the current community zoning maps, and also to strategically plan updates to the zoning maps to make sure that any areas where there is existing flooding risk are properly zoned. They can be rezoned for open area preservation or community parks, so that the natural function of the floodplains are maintained and the community is viewed to be, resilient to any flood risk, and also to minimize potential losses from flooding. Another application for the base level engineering analysis is for land development planning. Communities can use the base level engineering and all the data sets provided to regulate future planning and identify any existing flood buildings that are potentially of risk of flooding, and also protect any future developments from flooding. Well, the floodplain delineation provided by the base level engineering can identify the areas in the floodplain. Some of the additional base level engineering products can provide information that can better support the land development planning. And one of these products is the depth grids. So without having information about the depth grids, a planner or developer cannot identify the severity of flooding for a building proposed in the floodplain. As you can see on the images at the bottom of the slide, in the first image, building is being proposed to be placed closer to the channel where the flooding depths are higher, and respectively the consequences of flooding are going to be more severe. There will be higher potential losses, even for life and property. If the community officials implement the base level engineering data to permit this development, they can recommend placing this proposed building in an area, a shower area located toward the fringe of the floodplain, where the flooding depths are going to be less, so the building can be elevated with just adding a minimum fill in the area. Also, the house here is not going to be located near the channel where the velocities of during flooding are going to be significantly higher. So placing the building toward the edge of the floodplain where the flooding depths are less, we're going to be building a safer building here, and we'll have a reduced hazard to this proposed building. So again, along with the floodplain mapping, the depth grids for the various flooding events can be utilized to inform any future developments to minimize the risk of losses and of life and property. And with that, Sam will talk about the application of base level engineering analysis for public works planning.
Okay, thanks, Petya. So as Petya has been describing, we get a lot of great information out of these BLE studies. And one of the important items that communities can leverage is to look at the flooding, especially when it comes to public infrastructure, and look at the flooding extent to try to identify infrastructure that's at risk. So as Petya described earlier, with the BLE studies, when we come to roadway embankments, the culverts, the sizes of the culverts are not coded in, but rather the openings are estimated and they're burnt through the embankments. But then at bridges, at the bridges, you will get the bridge opening there. But what that will give us with the model results is you'll be able to go through and see where you have potential for overtopping for your roads. And with that, then you can start looking at some targeted capital planning, long-range planning for identifying any of these infrastructure at risk. Next slide. So when you as you go through, and there's multiple ways that you can go about looking at this, but again, the first cut is to use you can utilize and leverage the BLE to identify the overtopping roads. At that point, you've gone through and you've identified which ones they are. Now you can start looking at prioritization of them. So just using the standard risk equation, which is your likelihood times the consequence of the failure, and your likelihood of failure increases with your depth of flooding. So the higher the greater the depth of flooding, the greater the depth of flooding, then the greater the likelihood of failure for the roadway that you will have. Also, if the community has GIS inventory, then you could go through and overlay the inventory with these overtopping roads, and you could look at material ratings on them. You may have there may be condition assessment, inspection scores. And so when you combine your depth of flooding with your condition assessment to get some sort of like a pipe material rating or a bridge rating, then that there will be your likelihood of failure. And so you can start evaluating there. On your consequence of failure could be items such as the type of roads. If it's a more heavily traveled road, will have greater impacts to traffic. If it's the only way in and out of a subdivision, so that any sort of a failure from overtopping at those subdivisions would be a higher consequence. So again, you can go through and identify your projects, the overtopping projects, start scoring and identifying the likelihood or the frequency of overtopping, the depth of overtopping applies to that, and then on the consequences of failure, what would be impacted. And for there, you can start building a list. And then Once you get through that, if you have what a community can also do at that point is to repurpose the models. You could go through and collect additional survey data, code the structure in, be it a bridge, be it the culvert, go out and collect some basic survey data, code that in, and then refine the model. And then you can go ahead and refine your scores and your ranking for your structures. Next. And once you've identified your structures and identified the structures that could be overtopped, and you've gone through and you've ranked the more critical ones, at that point the communities can go ahead and start leveraging the models to do some concept planning. Like for instance, if you see that a roadway is overtopping and you go through and develop some sort of a rank list, you can start at the top of the list and then repurpose that model and start coding in and doing some concept planning to design to determine what type of structure is needed to meet your desired level of service. For instance, if a community's desired level of service is for all roads, all culverts and bridges to pass the 1% annual chance for 100-year storm without overtopping the road, then you can go through and look and see, what do we need to do here? Do we need to add additional barrels? Is it just a larger culvert or a larger bridge? Do we need to change the culvert out to a bridge? Or in some cases, the culvert may be big enough, but the roadway just needs to be raised somewhat in order to raise the profile of the roadway in order to provide additional freeboard or to prevent overtopping. Another item to look at, as I mentioned before, on the consequences are neighborhoods that may be cut off. There are a lot of neighborhoods where there's one way in and one way out. Well, if there's a stream or a river that goes through that neighborhood, the residents in the back of that neighborhood will be cut off if the roadway overtops and then if it's washed out. So those are some of the areas where you may go ahead and prioritize planning efforts there because there's greater impacts when it comes to potential for any failures or roadway overtopping. Next.
Thanks, Sam. So the base level engineering analysis can also be used for design to support H&H modeling developed for various development projects for engineers and government officials. Depending on where the proposed development is located in reference to the special flood hazard area and also to the base level engineering 1% floodplain, we have several scenarios shortly I will just highlight when base level engineering analysis can be implemented for design and when it's not recommended. So the first example that we're going to cover is a scenario where the land development project is adjacent but not encroaching on the effective special flood hazard area zone AE, or it's also not encroaching on the 1% base level engineering floodplain. If we have that scenario, it is recommended to use the effective base flood elevation for any regulatory purposes. Again, effective zone AE studies are using more detailed methodology than the base level engineering analysis. And until the maps are revised, the regulatory zone AE determined BFE are to be used for any development projects. The second scenario is if you have a land development that is adjacent but not encroaching on the effective special flood hazard area zone A, and it's also not encroaching on the base level engineering 1% floodplain. In this case, the base level engineering estimated BFE can be used for regulation purposes, unless you have a zone A with where base flood elevations are determined. The third scenario is if you have a land development project located outside of the effective special flood hazard area, but they're proposing to encroach on the 1% base level engineering floodplain. For that scenario, we recommend considering to evaluate the impact of the proposed development over the base level engineering elevations. And make sure that you don't have a negative impact on the water surface elevation upstream of the proposed development before issuing a permit for this development. Another scenario is if the proposed land development project is encroaching on the effective special flood hazard area zone A, or it's encroaching on the 1% base level engineering floodplain. And the base level engineering analysis is the only available study. In this particular case, we recommend utilizing the base level engineering data as the best available data and developing an engineering analysis, no rise analysis. So basically utilize the base level engineering, incorporate additional details. Again, if you have more detailed information about any structures, or if you want to add further detail into the, let's say, the Manning values for cross sections, or for the 2D watershed, 2D domain, if it's a 2D analysis, add further detail to develop a corrected effective modeling, and also incorporate the proposed modeling to develop a proposed plan, and compare the results of the two to ensure that the proposed development is not negatively impacting the water surface elevation at the site and upstream of the site too, and downstream too. And the last scenario is when land development projects are proposing an encroachment on effective special flood hazard area zone AE. As I mentioned previously, the zone AE studies are studied by detailed methodology approach. So for these cases, the FEMA effective models should be used to perform evaluation of the impact of the development. Application of the base level engineering analysis, one application for this scenario is to basically evaluate the topographic data embedded in the effective detail models. Some of the effective models are very old and they may use older topographic data or even quad maps topography, which is going to be outdated. So in these particular cases, you may just use the terrain data available with the base level engineering models to kind of check how does the cross sections in the effective model compare to the latest LiDAR topography data. You just need to keep in mind that probably the effective models are incorporated survey data for the channel sections of the cross sections, and the base level engineering analysis will not have that information because they're just simply based on the LiDAR data. So no bathymetry is being incorporated into the base level engineering. Base level engineering analysis can also be used to validate to some extent the effective hydrologic modeling. As I mentioned, the 1D base level engineering analysis are using a gridded hydrology methodology, and if you use that, you can basically determine the flow along the stream at every point of the stream. You can compare that flow to the effective hydrologic modeling. But you just need to keep in mind that the effective hydrology modeling can be developed by more detailed hydrology method like rainfall runoff models, and they may consider attenuation at some dams or like lakes and behydroed embankments, which is not going to be incorporated into the 1D base level engineering analysis. So to some extent, you can use the base level engineering analysis to validate the the effective flows, but again, use an engineering judgment when making the determination. Base level engineering analysis can also be used for other applications. Sometimes existing structures are placed on natural ground, but can be inadvertently mapped into the special flood hazard area. In this particular case, the base level engineering analysis can be used to file an application, a LOMR application, to remove this building from the special flood hazard area. So the estimated base flood elevation based on the base level engineering analysis can be used to submit a LOMR application to FEMA. And FEMA will grant the removal if the lowest adjustment grade of the building is higher than the estimated base flood elevation determined by our analysis. The base level engineering can also be used for cases where for LOMR F applications or CLOMR applications too. If again buildings are elevated above the estimated BFE for at the site. Base level engineering data can also be used in elevation certificates preparation. Again, if buildings are elevated or not. For flood proofing certificates, in case where the building lowest floor is located below the estimated base flood elevation, and the building has been flood proofed. And lastly, to ensure compliance with some of the regulations to elevate any service equipment above the base flood elevation, you can use the base level engineering analysis results to show that the proposed building is in compliance with these requirements. And with that, Sam is going to talk about the dam break modeling.
Okay, thanks, Betty. Yes, so the what we're going to talk about here, just real quickly, with the dam break modeling is not that the BLE models will include any dam breach modeling. It's that communities can repurpose these to do dam breach modeling for emergency action plan development and response to any situations that may occur at a dam. So the Georgia Safe Dams program identifies a dam as any embankment that holds back water that's 25 feet or taller, or impounds 100 acre feet or more of water at the top of the dam. So there are dams out there still, even if they're not identified as a dam by the Safe Dams program, that still can have impacts to infrastructure. A small dam, for instance, that may not be in the inventory, be identified as a dam, could still, its failure could still impact infrastructure downstream. So the intent here is the message here is that these models can be repurposed to develop dam breach modeling. So as what we would recommend to do is to follow the Georgia Safe Dams program engineering guidelines for any dam breach models, and the breach modeling will be based on a sunny day dam failure due to overtopping. Basically, you block all the spillways, the principal spillway pipe, and any emergency spillway. Everything is blocked, and the reservoir is filled to the top of the dam. It's not a rainfall event. It's not a meteorologic event. It's as if someone went out there and put something in the end of the spillway pipe to plug it up, and then filled a bunch of dirt in the emergency spillway and blocked it, so that the reservoir filled over time, and then all of a sudden it breached. So we'd recommend following the Safe Dams guidelines for those parameters for developing any sort of a breach model. And then once you have that, then You can use it for rapid response, potentially for response to an incident that's occurring, for any sort of planning, such as emergency action plan development, for any dams that you may have. Next. Can you go back one? Okay. And then finally, one last way to leverage the base level engineering information is with sewer infrastructure for I&I, for infiltration and inflow. This is most public works, within your public works, most of your gravity sewer systems or your interceptor sewer systems are generally going to follow the streams and run down the floodplain. So one way that you can leverage the information from the BLE is to look at either the elevation or the depth grids that you have and overlay it with your sewer infrastructure that you may have in GIS. If you see that your interceptor sewer manholes are all of a sudden being encompassed and are mapped inside any of your depth grids or elevation grids, then those could be potential areas for inflow into your sewer system. So you can identify those, and this is more to help out public works agencies with your I&I program to help prevent any sort of sewer spills. Next. And we have one more poll question. Can base level engineering be used in support of letter of map amendment submissions in effective Zone A areas?
And just a reminder to everyone, please answer the question if you are looking for CFM credits. Okay, it looks like we're winding down on responses. If you want to go ahead and close that out, Jim. Yeah, okay, we're here at the final stretch on questions. Please be sure if you've got any questions that throw them in that chat. I do have one for Petty real quick. If BLE data is available, can you use it in Zone AE areas?
So the short answer is no. So the base level engineering analysis I mentioned is a cost-effective way of calculating base flood elevations in various areas in the watershed. Though the Zone AE areas are developed by detailed H&H analysis, where more detail is incorporated, survey data is collected. So the base flood elevation determined in the Zone AE areas are still going to be the regulatory elevations, and they have to be used for any floodplain management regulations in these areas. As I pointed previously, some details from the base level engineering analysis can be utilized, like the available topographic data, because it incorporates latest topographic data and high detail topographic data to kind of supplement if somebody's evaluating no-rise analysis or something, they can use the newer topographic data for their analysis, but that's the extent of the application of the base level engineering for detailed studies.
Okay. And Sam, how would a community determine if a dam is regulated by the state?
Well, like I said earlier, the state defines a dam as any embankment that impounds water that's 25 feet tall or stores 100 acre feet or more of water. And so that right there would define it being a dam in the eyes of the state. But there are other guidelines out there. There's several guidelines that the state has, and I'll put in the chat. And the state actually has an inventory of dams that they have posted on their website. But I'll place in the chat the link to the Georgia Safe Dams program, and there's several resources out there, including the engineering guidelines and the inventory of dams.
Great, thank you so much. And with that, we're running a little short on time, so I don't want to have anybody not feel like they can't ask a question, but please be sure to put that question in the chat box. And if you would go ahead, yeah, we mentioned earlier that there are several resources for communities. Of course, you know, my favorite one and the one I'm always promoting, georgiadfirm.com, as well as some of the folks that are here today speaking to us, Sam and Petia, and my boss, Hayden, Joe, and Shannon also are very, very helpful folks and very knowledgeable on all of this information. So if you do have any more questions, feel free to reach out to any of us, and we'll try and help work you through all of that. And our next Lunch and Learn is on November 2nd from 12 to 1. So please be sure to mark your calendars. Note the Eventbrite invitation there. If you don't catch it, but it is in the chat, so please be sure to try and grab that. We'll also send out invitations as well. And next, make sure that you note the survey as well. Jim will also be putting that in the chat and try and get that completed, because that really does help us improve these webinars for future folks. And finally, we are offering one continuing education credit for today's session, available to certified floodplain managers that completed the polling questions and provide us their name and email address in the chat now. And finally, a copy of the presentation will be emailed to all attendees if you're requesting continuing education credits. Those certificates will be emailed separately. Once more, our next Lunch and Learn is scheduled for November 2nd, and please, please, please mark that on your calendars. With that, thank you again for attending today's event. And for those of you who don't have any further questions, this is the end of our Lunch and Learn webinar today. Thank you so much for attending, and have a great day, everybody.